The Drake equation, estimating the existence of alien civilizations. The Drake equation, estimating the existence of alien civilizations. Are we alone in the universe? This question has intrigued humans for centuries, and our quest for answers has led to countless stories, theories, and speculations about extraterrestrial life. But how? Can we scientifically estimate the likelihood of the existence of alien civilizations? This is where the famous Drake equation comes into play. Developed by American astrophysicist Dr. Frank Drake in 1961, the Drake equation is an attempt to estimate the number of technologically advanced civilizations that may exist in our Milky Way galaxy. By considering multiple variables, the equation offers a framework for scientists to ponder the probability of alien life. The Drake equation takes the form n equals r fp ni fl phi fcl. Let's dive deeper into the factors of the Drake equation and explore how they contribute to our estimate of the existence of alien civilizations. The first variable, r, is the rate of star formation in our galaxy. The Milky Way is estimated to produce around 7 new stars per year, meaning new potential homes for life are continuously emerging. However, it's important to note that not all stars are alike, and not all can support life as we know it. The next variable, Fp, considers the fraction of stars that have planets. Astronomical data gathered over the last few decades has shown that planets are abundant in our galaxy. With the discovery of exoplanets, planets outside our solar system, scientists estimate that around 20% to 50% of stars may have planets orbiting them. This suggests that the conditions for planetary systems, which ULD potentially harbor life, are more common than we once thought. Moving on, Ni takes into account the average number of planets per star that can support life. This factor considers the habitable zone around a star, where conditions for liquid water and potentia life are favorable. The discovery of exoplanets within this habitable zone has increased our optimism about the possibility of finding Earth-like planets with the potential for life. The following variable, Fl, is perhaps one of the most uncertain factors in the equation. It represents the fraction of suitable planets where life actually emerges. Despite our best efforts, they not yet discovered any conclusive evidence of extraterrestrial life, let alone complex organisms. The origin of life on Earth remains a mystery, so estimating the likelihood of life emerging elsewhere here is still highly speculative. Once life does emerge, however, we come to the factor phi, which represents the fraction of life that evolves into intelligent beings. The evolution of intelligent life on Earth has taken billions of years, implying that this step may be a significant bottleneck in the emergence of advanced civilizations. Whether or not intelligence is a common outcome of evolution is still unknown. Assuming intelligent life does arise, Fc comes into play. This variable represents the fraction of civilizations that develop advanced technology. This factor considers the societal and cultural advancements necessary for civilizations to reach a level of technological sophistication capable of communicating across vast distances. The timeline for such developments can be highly unpredictable and variable from civilization to civilization. Finally, we have L, which represents the average lifespan of a civilization. This factor reflects the longevity of technological civilizations. By multiplying these variables together, the Drake equation assists scientists in estimating the number of technologically advanced civilizations in our galaxy. However, it's important to emphasize the values assigned to these variables are largely speculative and based on limited knowledge. Currently, with the ongoing exploration of exoplanets, we are gathering more data and improving our understanding of these variables. As our technology advances, our estimates within the Drake equation may become more refined, increasing our chances of estimating the existence of alien civilizations more accurately. In our quest for answers about extraterrestrial life, the Drake equation has played a crucial role. Developed by Dr. Frank Drake in 1961, this equation seeks to estimate the number of advanced civilizations that may exist in our Milky Way galaxy. By considering several variables, it provides a framework for scientists to contemplate the probability of alien life. Let's further explore the factors of the Drake equation and how they contribute to estimating the existence of alien civilizations. The first variable, R, represents the rate of star formation in our galaxy. With an estimated production of around 7 new stars per year, new potential homes for life continually emerge in the Milky Way. However, not all stars are capable of supporting life as we know it. Next, FP represents the fraction of stars that have planets. Over the last few decades, astronomical data has shown that planets are abundant in our galaxy. Moving on, Ni takes into account the average number of planets per star that can support life. This factor focuses on the habitable zone around a star, where conditions for liquid water and potential ally life are favorable. With the discovery of exoplanets within this habitable zone, our hope of finding Earth-like planets with the potential for life has increased. The variable FL represents the fraction of suitable planets where life actually emerges. This factor remains highly speculative since we have not found conclusive evidence of extraterrestrial life. The origin of life on Earth itself remains a mystery, making it difficult to estimate the likelihood of life emerging elsewhere. Once life does emerge, Phi comes into play, representing the fraction of life that evolves into intelligent beings. The evolution of intelligent life on Earth has taken billions of years, suggesting this step may present a significant bottleneck in the emergence of advanced civilizations. Whether intelligence is a common outcome of evolution is still unknown. Assuming intelligence arises, FC represents the fraction of civilizations that develop advanced technology. This factor considers the societal and cultural advancements necessary for civilizations to achieve technological sophistication capable of communication across vast distances. The timeline for such advancements can vary greatly from civilization to civilization. Finally, we consider L, which represents the average lifespan of a civilization. This factor reflects the longevity of technological civilizations. By multiplying these variables together, the Drake equation assists scientists in estimating the number of technologically advanced civilizations in our galaxy. However, it's crucial to acknowledge that the values assigned to these variables are speculative and based on limited knowledge. As we continue to explore exoplanets and advance our technology, we gather more data and refine our understanding of these variables. This ongoing progress allows for more accurate estimations of the existence of alien civilizations. In our search for answers about the existence of extraterrestrial life, the Drake equation has been a valuable tool. Developed by Dr. Frank Drake in 1961, this equation attempts to estimate the number of advanced civilizations that could potentially exist in our Milky Way galaxy. By considering various factors, it gives scientists a way to analyze the likelihood of alien life. Let's delve deeper into the components of the Drake equation and their contributions to estimating the presence of alien civilizations. The first variable, denoted as R, represents the rate of star formation in our galaxy. The Milky Way produces approximately 7 new stars each year, meaning that new potential homes for life are consistently being formed. However, it's important to recognize that not all stars are capable of supporting life as we know it. The subsequent variable, FP, refers to the fraction of stars that have planets. Over the past few decades, astronomers have gathered substantial evidence pointing to the abundance of planets in our galaxy. Moving forward, Ni takes into account the average number of planets per star that could sustain life. This factor considers the habitable zone surrounding a star, where conditions for liquid water and potentially life are favorable. The identification of exoplanets within this habitable zone fuels our optimism regarding the existence of Earth-like planets with the potential for life. The subsequent term, FL, is arguably one of the most uncertain components in the equation. It represents the fraction of suitable planets where life actually emerges. Despite our extensive efforts, we have yet to discover any definitive evidence of extraterrestrial life, let alone complex organisms. The origin of life on Earth itself remains mysterious, making it highly speculative to estimate the probability of life arising elsewhere. However, assuming that life does emerge, we reach the factor phi, which depicts the fraction of life that develops into intelligent beings. The evolution of intelligent life on Earth has taken Billy